Greetings everyone, this is Professor Roman. Let's continue the group theory lectures. We have been discussing some groups and some families of groups. We talked about the cyclic groups, we talked about the Euclidean group, we talked about the family of dihedral groups, and I want to conclude this chapter, chapter 7, with a discussion of the additive rationals. So that's the rational numbers under addition. In general, determining the subgroup lattice of a group can be quite difficult. But here is an example of an important group whose subgroup lattice, while it is a bit complex, can still be determined with a little bit of effort. So we'll let Q be the additive group of rational numbers, and we want to analyze the structure of an arbitrary, non-trivial subgroup S of Q. Now the analysis will be easier to follow if we introduce some terminology. So first we'll say that an expression A over B, where A and B are integers, is in reduced form if A over B, A and B are relatively prime, but also if B is greater than 0. So any negative signs go in the numerator. And of course, any rational number can be expressed in reduced form. We will also say that a positive integer B is a denominator in S if B is the denominator for some reduced fraction, A over B, that belongs to S. And similarly, an integer A is a numerator in S for the denominator B if A over B is a reduced fraction in S. The denominator set for S is the set capital D of all denominators in S, and the numerator set for an element B in S is the set n sub B of all numerators in S for the denominator B. Now we have the terminology we need, we can begin. Suppose that B is a denominator in S. To determine which integers lie in the corresponding numerator set, first notice that if A is a numerator for B, A over B is in S, B times A over B is in S, and so A is in S. In other words, every numerator for B belongs to the subgroup S. So the thing to remember is all numerators of reduced fractions in S also lie in S. The most interesting integer in S, we know that there are some integers because the numerators are integers. The most interesting integer in S is an extreme witness among the integers in S. And in this case, that will be the smallest positive integer in S, which I'll denote by Z sub S. That doesn't depend on any numerators or denominators, it just depends on the subgroup S. You look around S, you find the smallest positive integer. Dividing any numerator, A, for a denominator B, by this smallest positive integer, we'll give this expression, the remainder lies here. Solving for R is non-negative, it's equal to A minus Q ZS, but A is in S, and Z sub S is in S, and so R is in S. But then the minimality of Z sub S implies that R has to be 0, and so our numerator is QZS. And since A and B are relatively prime, Q and B are also relatively prime, ZS and B are also relatively prime. So our numerator A is of the form QZS, where Q and B are relatively prime. Now, whenever we encounter relatively prime integers, we should think about Bezo's identity. So in this case, we know that there are integers u and v for which uq equals vb, uq plus vb equals 1, and so z over b is equal to 1z over b, which is this expression. You split it up. QZS over b is a over b. A over b is in S, ZS is in S, this whole thing is in S, so this special integer, this extreme witness, ZS, is a numerator for b, and in fact b was an arbitrary denominator, so ZS is a numerator for all denominators. But it follows from this that QZS is also a numerator for b, as long as Q is relatively prime to B, so we don't have any reduction. So QZS over B is already reduced. Well then, we have determined the numerator set for B. It is the set of all QZS where Q and B are relatively prime. And from that, we get a description of the subgroup S. It's the set of all QZS over B, where B is a denominator in S, and Q and B are relatively prime. But there is an unfortunate problem, the only problem, and that is we don't yet have a handle on the denominator set D. So we have to look at that. And in thinking about the denominator set, we can make some simple observations. First, all denominators in D are relatively prime to the integer ZS, because ZS is a numerator for every denominator, so that's a reduced expression. Closure under factor. If D is a denominator, then any factor of D is also a denominator. D is closed under relatively prime product. If we take two denominators, B and C, that's right, then ZS over B is in S, and ZS over C is in S. So their sum will lie in S, and their sum looks like this. Now, in general, this might not be reduced, so we can't jump to the conclusion that BC is a denominator. But if B and C are relatively prime, then this is a reduced fraction. So if B and C are denominators and they're relatively prime, then the product is a denominator. Now these two facts, number 2 and 3 here, tell us that the denominator set is in fact the set of all products of the prime powers that lie in D, the prime power denominators, because those can be multiplied together to get a denominator, and any denominator can be factored into a product of distinct prime powers, and each factor is a denominator. So all we have to do at this point then is figure out which prime powers belong to the denominator set. And to this end, let's suppose these are the prime integers in increasing order, P1, P2, and so on. If m sub I is the largest non-negative exponent of p sub I, for which p sub I to the mi is a denominator, then we know that the prime powers, that the powers of p sub I that lie in D are precisely these powers. because all factors of p sub I to the mi are denominators. All of these lower powers of pi are denominators, no bigger power. So this is precisely the set of denominators that are of the form pi to a power. Now there might be no maximum, no largest exponent. It's possible that all powers of pi are denominators. So in that case, we'll set mi equal to infinity. And let's refer to this sequence of maximum exponents in the same order as the primes as the maximum prime exponent sequence for the subgroup S. That seems a reasonable name, even if it's a bit long. So D is in fact the set of all products of prime powers whose exponents do not exceed these maximum limits given in this expression. Also, since the denominators in D are relatively prime to Z sub S, any prime factors of Z sub S cannot divide any denominator, because that would then divide a numerator of a reduced fraction, so it can't divide a denominator. Another way to say that is to say that if pi divides zs, then mi must be 0. So no prime power other than pi to the 0 would divide a denominator. Now, just for convenience, I'm going to make this definition here. Again, we have the prime integers. If z is a positive integer, we'll say that the sequence m sub z, that looks like this, for which the mi's are between 0 and infinity, including infinity, but with this property we just talked about, pi divides z implies mi is 0, we'll call that an admissible sequence for the integer z. It's not a very useful term. It's not a very intuitive term, but I couldn't think of a good one. And we're only going to use this just in the description of our final theorem, so it's not too critical, but it would be useful. So just as an example, if z is 2 times 3 squared times 7, then the admissible sequences for z are the sequences where the mi's are between 0 and infinity, but m1, m2, and m4 have to be 0, because m1 corresponds to the first prime, p1, which is 2, and that appears here as a factor of z. The second prime, p2, is 3, that appears here, so m2 has to be 0. And the fourth prime, p4, is 7. That appears here, so m4 has to be 0. So we know now that the maximum prime exponent sequence, ms, for a subgroup is admissible. It's admissible for this special integer, the extreme witness, z sub s. So now at last we can give a complete description of the subgroup S. We need a little bit more notation. If b is an integer, then I'm going to write ei square bracket b to denote the largest exponent of pi that divides b. So pi to the eib divides b, but when I kick the exponent up by 1, it no longer divides b. I had a different notation for this earlier, but I used an m in that notation. It would be very confusing here because we were already using m for maximum exponents, so I needed a different notation. if the subgroup S has smallest positive integer ZS, and if MS is the maximum prime exponent sequence, then the subgroup is the set of all fractions QZS over B. Q is an integer, B is a positive integer, Q and B are relatively prime, and the maximum exponent of PI in B here is less than or equal to MI. So that is a description of S in terms of ZS and MS. These two integers, the smallest positive integer in the subgroup, and the maximum prime exponent sequence, so you have to figure that out, but they completely determine the subgroup S. So we have a satisfactory, although a bit complex, description of an arbitrary subgroup S of Q in terms of the integer ZS and the sequence MS. Well, this makes us wonder whether all positive integers Z and all admissible sequences MZ for Z define what would be necessarily unique subgroup via this expression here. And to see that's the case, all we have to do is show that this set is a subgroup of Q. It's pretty clearly closed under negatives because Q is any integer, so it can absorb the negative if you switch the sign. As for closure under addition, if we have a QZ over B in S and an RZ over C in S, so we have two fractions of this form in the set S, and if I set G equal to the greatest common divisor of the denominators, B and C, and L the least common multiple of the denominators, then of course we know that BC equals GL. And so the sum of these two members of S looks like this, and I can divide numerator and denominator by the greatest common divisor of C and B. So I write this to still have the least common multiple in the denominator. Stuff in the numerator is an integer, so I can write it as UZ over L. U is an integer. Now, whether or not this expression requires further reducing, the exponent of P sub I, that's called E sub I, say the exponent E sub I of P sub I, in the reduced denominator will be no larger than the exponent of P sub I in either of these two factors. The exponent of P sub I in L is the bigger of the two exponents of P sub I in B and C. But when you reduce, you don't increase any exponents. You may or may not decrease them. So EI is less than or equal to the maximum of these largest exponents for B and C, and that's less than or equal to MI. So the sum belongs to S. It fits this condition here. So, after all this effort, we have a complete characterization of the subgroups of Q. The subgroup S of Q has smallest, if a subgroup S of Q has smallest positive integer ZS and if ms is the maximum prime exponent sequence for S. So we have to look at all the primes. For each prime, we have to search through all the denominators that are powers of that prime, pick the largest exponent, which could be infinity. Then S has this form. So that describes S completely, even though one would wish for something simpler, but at least it's a complete description. So ZS and MS completely determine the subgroup S. And conversely, we have our primes, we have a positive integer Z, we have an admissible sequence for Z, and this is what that means. MIs are between 0 and infinity, and if a prime P I divides Z, then the MI has to be 0. Then this set is a subgroup of Q. So we have characterized the subgroups of Q. And in the exercises for the book, I ask you to describe the order relation on sub Q. It's very interesting. It involves these admissible sequences. Okay. So that concludes the material in Chapter 7 of the book. And in the next lecture, we will move on.